All right, strap in everyone, because today we're going deep on Topos theory,
Oh, yeah.
which sounds like, I don't know, something out of like a science fiction novel.
It does, doesn't it?
But it's having a pretty big impact on the way that we are understanding quantum mechanics these days.
Yeah, I mean, it's really changing how we think about space and logic and even reality itself.
It's a little bit intimidating, to be
Uh,
honest with you, but we've got some academic papers to guide us through this.
Absolutely.
So hopefully that'll kind of keep us on the straight and narrow. So
Yeah.
what is Topos theory? Give me the elevator pitch.
Well, imagine a world where, like, the laws of physics change depending on where you are.
Okay.
That's what Topos theory helps us understand. It helps us understand how to make sense of a world where the rules change depending on your perspective.
Okay, so less about like finding answers and more about asking better questions.
Exactly. Topos theory is about deepening our understanding of the questions themselves.
All right, so where do we even begin with this?
Well, let's start with what we'll call the quantum playground.
The quantum playground. Okay, I like it.
So, quantum mechanics is notoriously difficult to understand, right?
It is.
But Topos theory gives us this framework, this mathematical framework, to kind of understand it in a way that feels more intuitive, more connected to our everyday experience.
Okay, so less about mind-boggling paradoxes and more about making sense of the quantum world.
Exactly.
How does it do that?
One of the key concepts here is this thing called the spectral preshift.
Okay.
And you can think of it like this. It's like a map that assigns to each classical context a set of possible values for a physical quantity.
Okay, so like if I change the context,
Yeah,
a set of possible outcomes changes.
exactly. It's like a choose-your-own-adventure for quantum mechanics.
All right, I'm with you.
Now, in traditional quantum mechanics, we always have this problem, right?
Mm-hmm.
That the act of measuring something changes what we're measuring.
Right, like the particles that don't know if they're a wave or a particle until we look at them.
Exactly. But in Topos quantum theory, we don't need measurement to define truth.
Oh,
Truth is relative to the context. So we can kind of bypass those paradoxes, right? Where you measure something and it changes the outcome because
so instead of like searching for this single absolute truth, we're kind of embracing the idea that it can be context dependent.
Exactly. And this has some profound implications, even for something as fundamental as the Koch and Specker theorem.
Okay, remind me about the Koch and Specker theorem.
Basically, it says you can't consistently assign definite values to all physical quantities in a quantum system. It's like trying to create a map of a city where the streets constantly change their layout depending on how you look at them.
So no imposing our kind of classical views on the quantum world.
Yeah, you can't really do that. But Topos theory reframes the Koch and Specker theorem.
Okay.
Instead of talking about inconsistencies, we talk about the lack of what are called global sections in the spectral presheaf, which would be, assigning consistent values.
Right.
Says they don't exist.
So it's not that there's something wrong, it's just that there is no like one correct way to look at it.
Precisely.
Okay.
And that leads us to another interesting concept, which are called locales.
Locales.
Yeah, so imagine trying to describe a city, right, without listing all the individual buildings.
Okay.
But instead, you talk about its neighborhoods and how they're connected. That's what locales are like.
Okay, so it's like a more abstract way of talking about space.
Yeah, more relational.
Hmm.
Now, the spectral preshift we talked about actually has an internal locale associated with it.
Okay.
And this locale has some interesting properties. It's compact, but it's not regular.
Okay, unpack those terms for me.
So compactness is like a finiteness condition.
Okay.
Even if you have an infinite number of things, you can still cover it with a finite number of open sets. And this has some interesting connections to like ancient philosophy, right?
Okay.
Like Aristotle argued against the possibility of infinite motion in a finite time.
So we're bridging ancient philosophy and modern physics here.
We are. Now, the fact that these locales are not regular, that means they don't have this property where you can kind of neatly separate points using open sets.
Okay.
So they're a bit rough around the edges.
So they're not as predictable as the spaces we're used to dealing with in classical math.
Exactly. And this roughness actually has a profound consequence, right?
Mm-hmm.
It means these internal locales can't be represented as the spectrum of something called a C algebra, which is a very common mathematical object used to describe quantum systems.
So Topos theory is revealing aspects of quantum reality that, like, go beyond our conventional math tools.
Exactly. It's like discovering a new continent, right, with its own unique laws of nature.
Yeah, it's a little bit daunting, but very exciting at the same time.
It is. It is.
So Topos theory isn't just giving us new answers.
Right.
It's like giving us a whole new way to look at the universe.
Absolutely. And as we go further, we'll see how this new perspective can shed light on some of the most fundamental questions about reality itself.
Okay, I'm ready. Let's go.
All right. Welcome back to our deep dive, into this really strange world of Topos theory.
Yeah, last time we were talking about how it helps us understand, the structure of space in a whole new way, right?
Yeah.
Using those locales that are like point-free.
Right, exactly.
And, you were mentioning that the internal locale associated with the spectral presheaf is both compact and non-regular.
Right.
And I'm still trying to wrap my head around those concepts.
Yeah.
And what they really mean for quantum mechanics.
So compactness, just to remind you, it's like a finiteness condition.
Okay.
Even when we're dealing with infinite sets.
Okay.
It means we can, cover the entire locale with a finite number of these open sets.
Okay, I see.
It's a bit like if you imagine you have a map, right?
Yeah.
And you want to map out an entire continent. Even if it has infinitely many details, you can still do that with a finite number of maps, if you just zoom out enough.
Yeah, okay, I'm starting to get the picture.
Yeah, so there's this sense in which even though these locales might be incredibly complex,
Right.
there's still this a kind of boundedness to them.
Okay.
And, like I said before, this idea of compactness, it has some really interesting connections to ancient philosophical debates about infinity. Like Aristotle, for example, argued against the possibility of infinite motion in a finite time.
Right.
So this concept of even in a space with infinite possibilities, there's a certain kind of finiteness to how those possibilities are structured.
So we're seeing echoes of these really old questions.
Yes.
In the fabric of this theory.
Exactly.
That's pretty amazing.
Now, the fact that these locales are not regular,
right.
Remember, regularity means we can neatly separate points in closed sets using open sets.
Okay.
It's a property that ensures a certain kind of smoothness. But in these internal locales, that kind of separation isn't always possible. So they're a bit rough around the edges, so to speak.
So they're not as well behaved as the spaces we're used to dealing with.
Exactly, precisely.
In classical mathematics.
They're less predictable.
Okay.
And this roughness, as we discussed earlier, has a profound implication.
Okay.
These internal locales, they can't be represented as what we call the spectrum of a C algebra, which is this mathematical object that's often used to describe quantum systems.
Okay, so we're going beyond the reach of our conventional tool.
Absolutely, yeah. Topos theory is revealing aspects of quantum reality that lie beyond.
It's pretty exciting, though.
It is.
We're pushing the boundaries.
We are. And this brings us to another area where Topos theory really shines,
right.
which is quantum logic.
Quantum logic?
Yeah. So remember those Birkhoff-von Neumann lattices?
Remind me, please.
Yeah. They're blueprints for how propositions are connected in quantum mechanics.
No.
And one of the key differences between classical and quantum logic is that classical lattices are distributive, meaning we can kind of rearrange the order of certain operations without changing the outcome.
Right.
But quantum logic lattices are not always distributive.
Okay, so there's a kind of ambiguity.
There is,
so it's the quantum world is just playing by different rules.
It is, for logic.
And this is where Topos theory comes in with a brilliant move, right?
Okay.
It allows us to embed these non-distributive quantum logic lattices into a complete Hating algebra.
Okay, what is a Hating algebra?
Hating algebra is a mathematical structure that kind of generalizes the notion of a lattice.
Okay.
It's a bit more flexible. It allows for a wider range of operations, logical operations, and relationships.
Right.
And crucially, Hating algebras can accommodate those fuzzy truth values that we talked about.
Yeah.
Those shades of truth that go beyond the simple true or false.
So we're moving from a black and white view of truth to a more nuanced, multi-valued logic.
Oh.
And by embedding quantum logic into a complete Hating algebra, Topos theory does two things, right? It demonstrates that quantum logic is inherently richer and more expressive than classical logic.
Okay.
And secondly, it provides a bridge between these two seemingly disparate logical systems, showing how they fit within a larger, more encompassing framework.
So it's not just about getting new answers.
Right.
It's about like a whole new set of tools to think about the questions.
That's a great way to put it.
Yeah.
Absolutely.
Absolutely great.
And as we move forward, we'll see how these tools can be applied to some of the most profound mysteries of the quantum world.
All right, let's dive in. Okay, so we've really gone pretty deep on this Topos theory stuff.
We have.
We've covered quantum playgrounds, logic-defying rules of the quantum world.
Yeah.
But there's one thing that I'm still kind of curious about, and that is, how does it approach the idea of a quantum state?
That's a great question. And it leads to, I think, one of the most profound insights of Topos theory,
Okay.
which is that instead of focusing on individual states,
Yeah.
it encourages us to consider the entire collection of possible states as a unified whole.
So instead of looking at a single point on a map, we're looking at the whole landscape.
Exactly. And this allows us to really study the dynamics of quantum systems in a much richer, more comprehensive way.
Right.
We're not just tracking a single particle moving through space. We're kind of watching how the entire fabric of possibilities shifts and transforms over time.
So we're watching how the whole quantum landscape evolves.
Exactly. And to do that, Topos theory gives us two really powerful perspectives, the covariant and the contravariant.
Two different lenses.
Yeah, two different lenses through which to view the quantum world.
Okay, I like it.
The covariant approach focuses on how states transform as we move forward in time.
Okay, so it's how does this unfold step by step?
Yeah, it's like tracing the path of a river as it flows downstream. The contravariant approach, on the other hand, takes a more kind of retrospective view.
Okay.
It's like looking upstream, trying to figure out where the river originated.
I see.
It focuses on how states can be pulled back from the future to the present.
So what are the potential pathways that could have led to this?
Exactly. And both of these approaches are incredibly valuable, right? They give us complementary insights into how quantum systems behave.
Yeah. It's like we're getting this multi-dimensional view, right, of the dynamic.
Absolutely.
How things are changing.
And the key to kind of unlocking this multidimensional view is understanding something called measures.
Measures. All right. So back to measures, but
Back to measures.
not measuring cups and rulers, right?
Not measuring cups and rulers, no. These measures are much more abstract.
Okay.
And powerful. They're mathematical objects that help us kind of assign values to different possibilities. Within the collection of states, you can think of it as a generalization of the concept of probability.
So instead of just saying, this has a 50% chance of happening,
Right.
we're using these measures to kind of describe a much wider
Much wider range.
of possibilities.
And they can handle situations where, our classical notions of probability completely break down.
Yep.
So it gives us a more nuanced and flexible language to describe the inherent uncertainty of the quantum world.
This is really kind of mind-blowing.
It is.
It seems like Topos theory isn't just about changing how we think about quantum mechanics,
Yeah.
but it's also changing how we think about logic and probability and reality itself.
It is. It's challenging us to kind of think beyond our classical intuitions.
Right.
And embrace a more holistic and interconnected view.
Well, on that note, I think it's time to wrap up our deep dive into this pretty incredible Topos theory.
It is incredible.
And I want to leave our listeners with one thought. This has been a whirlwind.
It has. Of mind-bending ideas.
Absolutely.
Surprising connections. We've seen how Topos theory bridges the gap between ancient philosophy and modern physics, reshapes our understanding of logic, provides new tools to explore the mysteries of quantum mechanics. And, this is just the beginning, right?
It is.
There's so much more to uncover in this fascinating world of Topos theory. So keep exploring, keep asking those big questions.
Yeah, don't be afraid to get lost in the math.
Yeah, get lost in the math. And who knows what incredible insights await in your Topos theory journey. So thanks for joining us.
Thank you.